Hi, everybody. Thank you for joining us for the seminar today. Our speaker today is Koushil Sreenath. He's a new faculty at UC Berkeley. He's assistant professor in mechanical engineering. He received his PhD in electrical engineering and computer science, and his master's degree in applied mathematics from the University of Michigan at Ann Arbor. He was a postdoctoral scholar at the GRASP lab in University of Pennsylvania, and was assistant professor at Carnegie Mellon University. His research interest lies on the intersection of highly dynamic robotics and applied nonlinear control. His work on dynamic leg locomotion on the bipedal robot Mabel was featured on the Discovery Channel, CNN, ESPN, Fox, and CBS. Hope you will show us some of that. Thank you.
Yeah, thank you, Ron. Thank you for the great introduction. I'm not going to show anything from Mabel. Yeah, sorry, I didn't know about this. Otherwise, I'd put in some videos. Oh, maybe there's one video. Yeah. So thank you for coming. I just realized that it's RSS deadline. So this is great that you're here. It was a long trip for me to get here from across the Hearst Avenue. And in between, I got lost a couple of times, but I finally made it. So today, I want to talk to you a little bit about my work on safety critical control applied to walking robots and aerial robots. My goal is basically to find out ideas from you for collaborations that would go on in the future years. All right, so I'm an assistant professor in mechanical engineering. So before I get started, I wanted to thank my collaborators, my funding agencies, and my students who worked on aerial systems, as well as legged systems. So why do we want to work on legged robots? So to motivate this, let me show you a video. So this is a video of a snow leopard chasing a mountain goat on extremely rugged terrain. And what you'll notice is none of these creatures miss a single step. Their foots don't even slip. And this is at high speeds. This is live action. These are amazing creatures. Our robots come nowhere to the performance capabilities of these animals. One of the goals that our lab has to enable robotic systems to operate at such high speed on extremely rugged terrain. Don't worry, it's a happy story. But actually, it's a sad story in a way. So people feel sad for the deer, but actually, it's the leopards that are going extinct. You don't realize that. So another research thrust that we have is to work on aerial robots. So to motivate why aerial robotics, let's talk about what's happening or what's going to happen in the next 5 to 10 years. So these are urban cities, densely populated. 75% of the world's population is going to be in these dense urban cities within the next 10 years. So this is great, but the only problem is if you want to transport anything within a city, it's super hard. We have scenarios all around the world that are tending to these traffic jams all around. So if you want to transport a small package, in terms of time, in terms of money, it's going to take a lot of inefficiencies. And one approach is to do aerial transportation. And this is nothing new. People have been working on this over the last 5 years. You see Amazon, Google, DHL, Matternet, and a whole bunch of other startup companies. But one thing that they're doing wrong is the following. So suppose I take a heavy load and I rigidly attach it to this payload. This increases the inertia of this payload. It makes the attitude response sluggish. So if you get hit by a wind gust, it's very hard for the controller to react to this. So you want to preserve the agility while also achieving the task. Another interesting thing here is if you want to increase the mass, pretty heavy, one solution is to increase the size of this aerial robot. But this becomes very unsafe to fly over urban environments. They're very noisy. They're also not very safe if they crash. So one solution that we're looking at is to have multiple aerial robots to transport a shared package. I spent a lot of time in Pittsburgh. I know a little bit about the history of Pittsburgh. So I'm going to talk about Allegheny Airlines, which later on became US Airlines, which got bought over by American Airlines. And here they're going to demonstrate transportation through a cable suspended package. So this is how rural Pennsylvania had their mail delivered in the 1940s. So you have drop off and pick up without ever landing the aircraft. And within 4 hours, all of Pennsylvania could be covered. This is the mail system back then. It's pretty amazing, right? 1940s. So once you can do this for small packages that are passive, the next obvious thing would be, any guesses on what else you can transport? I know Claire knows this.
Is made with a low-flying craft. Success in this experiment.
All right, so here is a scapegoat that was actually picked up, and here you see the animal is doing pretty well and safe. And once you can do animals, the next obvious thing is humans. So this is back in the 40s. Here's a soldier with nerves of steel. He's actually smoking a Marlboro. It's amazing that the pilot can actually pick him up, and he has to execute a high dynamic maneuver that has to go up. So we'll look at this in slow motion, and there's a lot of hybrid dynamics that come into play here. So the tension in the cable that picks him up has a huge amount of force, and then the force goes to 0 as the cable goes, tension goes to 0. And despite all this, this person has to be picked up, otherwise his back is going to bounce on the ground and shatter his bones. So this is an amazing thing that was done by a manned pilot. How do we do this with an unmanned aerial vehicle? That's another one of the goals that we're looking into. So the future of tomorrow will be this aerial robots all around the skies of our cities, transporting packages that are heavy and having safety through redundancy. So imagine the movie Up, replace all the balloons with small aerial robots. One of them fails, they become part of the payload. So today I'm going to talk about 2 of these problems, legged locomotion and aerial manipulation. So just to give you what this is, so safety critical control applied to legged locomotion. So you want to walk fast on a terrain that's made of these stepping stones. So if you miss a single step even by a few centimeters, your whole robot falls. So it's a safety critical constraint that has to be enforced while you are also respecting the dynamic constraints. The second problem, we want to design controllers that can track the position of the payload along a desired trajectory, not the aerial vehicle, but the payload. And there's a lot of under actuation because this cable is freely suspended, so you can oscillate. We want to solve the problem not only for a single aerial robot, for multiple aerial robots. So this is a challenging problem. The dynamics are complex. You have nonlinear dynamics, you have hybrid dynamics. For aerial systems, you have dynamics on manifolds. The controllers not only have to enforce a static equilibrium, but actually a periodic equilibrium that involves stabilizing to a periodic orbit. You need to achieve geometric control to give you global stability properties. So towards this, we'll look at control approaches that go along 3 different axes. So we'll start with standard controllers. We'll extend that along the constraints axis, the model uncertainty axis, and the safety axis. So we look at standard controllers that can work for nonlinear hybrid dynamics, for under-actuated systems, and for periodic orbits. Now we look at CLF controllers that can do this, control Lyapunov function. We'll extend this to control Lyapunov function-based quadratic programs where you can enforce additional constraints. We look at robust and adaptive formulations, which can enforce model uncertainty. We look at safety critical constraint using barrier functions. So this is like walking on stepping stones. And finally, we'll put all of these together to do constraints, uncertainty, and safety together at the same time. So first thing, let's look at the models for these 2 systems. So whether you take a legged robot or you take an aerial robot with a suspended payload, both these are described by hybrid models. So you have a nonlinear model, under-actuated. When the foot hits the ground, there's an impact map that transitions into the flight phase for running or for walking this particular thing. Similarly, when the tension in the cable is non-zero, your cable is taut, the tension goes to 0, your cable becomes slack, and you have a transition map that gets you back. So if you look at, let's say, one of these for aerial robots, these models are fairly complex. So for this system that I'm showing you, it has 4 quadrotors with a 5-link cable with a rigid body payload. This has 58 degrees of freedom. 42 degrees of those freedom are under-actuated. They're not actuated. So it's only the difference that you can control. You can develop the models for this. We can also develop controllers for these things. So once again, so you want to design controllers to track the desired trajectory, either for a single or multiple aerial robot. So let's dive into control design for a legged robot. All right, so here we have what are called mechanical constraints enforced through gears and links. And these constraints can be represented by an equation y. So you drive this y to 0, it enforces these constraints. Now this is a toy. For a robot, we don't have these links and gears, but you can enforce and create these constraints virtually through motors and feedback control. So I want to design a controller that drives y to 0 and y dot to 0. That's my control goal. An easy way to do this is to do input-output linearization, and you get a system which is linear in terms of the output. So the output dynamics is a linear system. A linear system, you can use your favorite linear controller. Here we'll use a simple PD control, and we can design a walking gauge for this system. So this would give you the hybrid zero dynamics component of the control. What we want is we also want to enforce constraints, safety, and model uncertainty. So let's look at how we can enforce constraints through control Lyapunov function-based quadratic programs. So let's go back to this. So with our control, what we have is a linear closed-loop system. If you have a linear closed-loop system, we can create a quadratic Lyapunov function. And if you design a controller that enforces this particular constraint on the Lyapunov function time derivative, your V goes down to 0 exponentially, the Lyapunov function, which means your output goes down to 0 exponentially, and then it enforces your goal. One controller that can enforce this is a min-norm controller, which is given by this. So as long as this is negative, your control action is 0. If this is non-negative, it takes the smallest control action to enforce that this is less than or equal to 0. So I'll show you a video where this controller was implemented on the robot Mabel. And you'll see that this part of the experiment, which was the input-output linearizing controller, this is the torques. They're going bang, bang, bang. There's a lot of noise. And once you switch over to the min-norm controller using the control Lyapunov functions, the torques are a lot more smoother. And more importantly, it's energy efficient. So try to listen to the robot here. All right, there's no sound here anyway. So here's Mabel that's walking around, and we switch over to the CLF-based controller. This controller is being executed at 1 millisecond, and it's a lot more smoother and more energy efficient. Now, once you have this control based on the CLF, you can also create this CLF-QP, which is exactly equivalent to the min-norm controller, which enforces this particular constraint, which is the same thing. Question?
So when for the Lyapunov function, this whole design is based on the input-output linearization of.
That's right.
Is it always possible for bipedal robots to do the linearization, or is it something about the structure of bipedal robots that allows us to do so?
So for these particular systems, it's possible to do input-output linearization. So there could be some designs where it's not possible. So you need to check for input-output linearizability. Okay, so once you have a quadratic program, you can also put in additional constraints. And these could be in terms of torque constraints, force constraints, friction constraints, and so on. So you can do periodic walking, where you can now enforce torque constraints that become stricter and stricter as your battery dies. So this is periodic walking, that's nominal. But as you make your torque constraints smaller, your constraints are enforced strictly, but then your tracking errors become larger. So you still achieve the task of walking, but at a lower performance. So your errors in this large thing are pretty high, but you still are walking. So here you're taking the constraints into account in your control design. Now you can extend this control Lyapunov functions to systems that evolve on manifolds. These are for aerial robots with suspended loads, for instance. So here you can look at the covariant derivative, which describes the dynamics of the system on manifolds. You can create a geometric Lyapunov function, and you can enforce this geometric Lyapunov function-based controls. So here's some examples. So this is the largest possible error for the system in terms of orientation. So the quadrotor is inverted, the payload is inverted, but the controller is still able to track this desired reference trajectory. You can do this for a single quadrotor with a suspended payload. You can do it for multiple quadrotors as well. Now we can also look at the case where you have a single aerial robot, but the cable is now not as one link, but it's made of multiple links. So here the goal of the controller is to make the payload follow this desired trajectory. So we started off with a hover configuration. In the next video, we'll start off with the inverted configuration. So there's a huge error in the attitude. The controller recovers from it, and it's still able to track this trajectory. So you have global stability properties for configuration errors and orientation. All right, so we've looked at control Lyapunov functions for quadratic programs. Now let's look at model uncertainty. So our group has looked at robust and adaptive formulations to address model uncertainty. I'll talk about one of those and present the results for the second one. So what we want to do is have walking robots that can walk without the controller being aware of this additional uncertainty that's added to your model. And this is not just an example that I picked up from the web. It's something that happens in real legged robots. So there's model uncertainty because your models that you derive are not always accurate. You have parameters because of you're carrying packages that you don't know. Your ground disturbances could be model perturbations. So there's a huge amount of uncertainty. And here's a video that's been overused from the DARPA Robotics Challenge. And I would say most of these failures are because of model uncertainty. So the methods that were applied didn't take into account the uncertainty. Almost every single robot in the DARPA Robotics Challenge fell, except one. So let's look into how we can address model uncertainty. So what we saw before, we had a linear system. And we can have a control Lyapunov function-based controller for this. Now, when you have model uncertainty, this linear system now has unknown parameters, which are nonlinear in terms of the model, unknown model. So you want to design a controller for this system where delta 1 and delta 2 are not known. If you make an assumption that these uncertainties are bounded, then you can design a controller based on the bound. So to take a look in terms of Lyapunov functions, so the Lyapunov function condition that we wanted to enforce was this. But because of uncertainties, now we have this new constraint that we want to enforce. If you make an assumption that these uncertainties are bounded, then if we enforce this max inequality constraint, then we can still guarantee convergence to 0 for the Lyapunov functions under these constraints. So your CLF-QP now looks of this form. And the key thing here is your Lyapunov function is still affine in terms of not only the control input, but also the model uncertainties. And this lets you implement this as a quadratic program. So here are some examples. This is numerical simulations on the left. So this robot is carrying a huge model uncertainty in terms of a mass. That mass varies at every step. And it varies between 0 to 95% of the mass of the robot. And the controller is not aware of this. The controller is still able to regulate and demonstrate walking motions. So we're looking at some experimental implementations. So here is a 70-pound mass that's attached to the robot. So we can stand, we can do a little bit of walking. We're trying to submit this as a journal soon. So we've seen legged robots. This controller can also be applied to aerial systems. So this is fast motions with large errors, large attitude maneuvers. So this aerial robot has a 100 mass payload, about 10 centimeters from the center of mass. And the geometric adaptive controller is still able to regulate and track a desired trajectory, that's a circular trajectory at 3 meters per second. All right, so we looked at model uncertainty. Now let's look at safety critical constraints. So this is stepping stones. So humans are very good at walking on stepping stones. Now you want to make robots do the same thing. So this little kid can also do this pretty well. Now on this last step, he actually does nail the stepping stone, but he's not able to account for the slipping. He's not able to account for the friction constraints. So he violates the friction cone and he slips. So when you design controllers for bipedal robots to walk on stepping stones, you not only have to enforce the constraints, safety constraints, but you also have to enforce the friction constraints. Now this is a very important problem in legged locomotion. There's an outstanding prize called the W prize. One of the tasks in the W prize is to walk over the cinder blocks. Now this is more complicated than the problem we are trying to solve because the cinder blocks can actually topple. So we assume that the cinder blocks are constant. So anyway, so we want to do the safety critical constraints in the form of walking over stepping stones. So our solution uses something called barrier functions, control barrier functions. So we looked at control Lyapunov functions. Now let's look at what are control barrier functions. So you want to enforce the constraint of the form given by this. B is always positive. And the way we can enforce the safety constraint is through the control input. So if you look at the time derivative of B, the time derivative of B, when it depends on the control input, would be of this form. And if you enforce this constraint on the time derivative of B, then your B is guaranteed to be positive. And to take a look at this, so let's say my B was initially this. If I'm enforcing this particular constraint, my state evolves such that I'm in this green region and I'm lower bounded by this red thing that goes exponentially to 0. So you're indirectly enforcing the safety constraint. So it's very similar to a Lyapunov function. The constraint that the only difference is you have a less than and then you have a greater than sign. Now it's possible that the barrier function may not have relative degree 1 as shown here. It could have higher relative degree. Then you need to look at higher time derivatives of the barrier function. And you can still enforce a constraint of this form. You can put both of these together to create a control barrier function, control Lyapunov function based quadratic program. So we want to do this footstep constraint placements. Now placing the swing foot on this stepping stone is an end time constraint. So the end of your stepping time, you want your foot to be on this constraint. One way to address this end time constraint is you can convert it into a constraint of this form. So at every instant in time, I want my swing foot's trajectory to be inside this bigger circle and outside the smaller circle. So as time evolves, eventually you end up on the stepping stone. So if I look at this vector O1 to F, I want it to be inside this big circle and outside the little one. And this can be enforced as a barrier function, 2 different barrier functions. So you can see simulations. This is of the model of a bipedal robot called Rabbit. So the controller is provided knowledge of only one stepping stone. So you don't know the entire terrain. As you take one step, your controller is given information on where is the next step. So you have to enforce a time critical safety of placing a swing foot to the next one. So this method also works on high-dimensional humanoid systems. This is 22 degrees of freedom, 44 states. Here, not only the step length is changing, but the step width is also changing. So we can also do more complex terrain. So here, not only the step length changes, the step height also changes. And here, all the robots have point feet. This is a model of the robot ATRIAS. It's pretty cool, right? Now, everything works in simulation. So here are some experiments. So these are very recent experiments. So here's ATRIAS that's working on cinder blocks. The controller is provided knowledge of one step ahead on where the stepping stone is. The stepping stones are distributed randomly. So step length changes every step. Here we are not using vision yet, but we are planning to use vision. So that was step length. We can also do step height. If you do things wrong, robots break. So here's an example where we can do step height. So once you have step length and step height, you can combine the two of them. So here are recent results where step length and step height vary randomly. And we have only finite amount of step height in the size of this cinder block, but we can still achieve walking dynamically at an average speed of 0.6 meters per second on this. So this control barrier functions can also be implemented on systems where the dynamics evolve on manifolds. So you can create geometric control barrier functions. And then now you can enforce safety critical constraints for quadrotor systems. So here's a planar quadrotor trying to avoid this obstacle. The goal is to follow the desired trajectory. There is no replanning in any of these two motions. It's a low-level controller that's guaranteeing safety. We have some preliminary experiments. So here you're trying to do teleoperation. So imagine you have a pilot, you're a learning pilot, you're not advanced. You have the safety constraints that you want to stay within this virtual box. The pilot commands, but if you know that you're going to violate a safety constraint, the controller would then override the commands from the user. And this is all done without any replanning. All right, so we've looked at constraints, we looked at model uncertainty, we looked at safety critical constraints. Now let's see if we can bring all of these together. So where you have robustness and you have safety constraints. So the idea is to merge the results from this as well as stepping stones. Now, if we look at the time derivative of B dot, which is a barrier function, it's dependent on the model uncertainties in a similar way that the Lyapunov function is dependent on this. Once again, we can make an assumption that your unknown parameters are bounded, and you can create this max inequality. So now we have this huge, robust control Lyapunov function, control barrier function based quadratic program, where you can solve this and enforce constraints for robustness while also giving stability and safety guarantees. So we have some simulations and some preliminary experiments. So here's a non-robust controller that fails within one step, whereas a robust controller that has almost 50% of model uncertainty is now walking on a terrain with mobile stepping stones. So this is sort of like Indiana Jones from the Temple of Doom. So he's going from one stepping stone to another while carrying something really heavy. So I'll show you some preliminary experiments just to demonstrate that this actually works in experiments. So here's a small cart. The goal of this is to drive from this position at 0 to the goal at 2. But now you have a safety constraint to avoid going past 1. So we take the system, we throw in a huge amount of model uncertainty. So you can put in a huge amount of load, you put in unknown dynamics with a trailer, you put in unknown disturbances, and now the controller can still enforce the safety constraint. So if you look closely here, so you see this position does not violate safety constraint of 1. So your cart position is always upper bounded by this 1. So your controller enforces that you're always below this, despite all the model uncertainty that's coming into the system. So we have good results on safety critical control with model uncertainty. Now let's see if we can combine this with perception. So where we are headed is towards safety critical perception. So if you have control, that works really well, but if your perception module gives you the wrong estimate, when you combine the two, you can no longer enforce a safety constraint. Now perception is a hard problem. So if you look at an onboard view, you're trying to place your feet on these stepping stones. You can hardly see the stepping stone that you're going to place your foot on. You can only see a few steps ahead. So a few simplistic vision examples on this. So we have a camera here that's mounted. It's doing a simple depth segmentation that finds out these stepping stones, and you can still place your feet on these. What we want to do is we want to combine this with deep learning. So where you have a CNN that does the perception, provides you some guarantees on its estimate, and then you combine this with the controller that provides safety guarantees. So can we generate synthetic terrain data, feed this through a CNN, provide a model, get a model, and then do experiments with this? So we've generated synthetic data with various amounts of textures for the background and foreground, created the simplistic network with 6 layers. It's got 3 CNN and 2 fully connected networks. Now the goal here is to design and train a network where the worst case is bounded. So if you work in deep learning, you can get a very good mean in your estimate, but it's possible that a few estimates could be quite off. But even if you get one single thing that's off, and you send that to your controller will try to enforce that wrong estimate, and your safety constraint will be violated. So here, what we've done is we're trying to train the network so that we can upper bound the error to some extent, and this was done manually. So here's some of the best predictions. It generalizes fairly well over texture, exposure, and shadows, and it does pretty poorly on long shadows and reflections. We can test all of this in simulations. So you can combine a fairly accurate dynamical model in MATLAB. You have Blender that synthetically generates this terrain data. You have TensorFlow that takes this visual input and spits out the step length to take next. You have a safety critical controller that's running, and you close the loop, and what you get is a perception model with the safety critical control. So we're still working towards providing guarantees for perception. So here you get each image for every step. It's very hard to see here. You can see the predicted and the actual ground truth of your step estimate. So we have all these results on legged locomotion. And we're trying to see if we can translate these to exoskeletons. So here's an example. We're working with a French startup company called Wondercraft. Some simulations, some very preliminary experiments. So I've shown you a lot of things in legged locomotion. We have results on stepping stones with dynamic motions. We have results on aerial manipulation that cover a whole bunch of different cases. So I wanted to spend some time to get some ideas, to get some thoughts for future collaborations. So thank you for listening to me. Happy to take any questions.